All right, we're going to finish off 15.2 and 15.3. So this will cover Lewis acids and bases, formation constants, and coupled equilibria. So what are our objectives? We will review the definition of Lewis acids and bases. We will write equations representing these types of acid-base reactions. We'll perform equilibria, calculations involving Kf, which is the formation constants. We will describe systems that involve two or more coupled equilibria, and finally, we will calculate reactant and product concentrations from coupled equilibria systems. From the previous slides on formation constants, we recall that formation constants were taking a Lewis acid, putting it together with a Lewis base, and making an acid-base adduct. And so we have the acid-base adduct over the Lewis acid over the Lewis base. And you can have those in different proportions, right? You can have multiple Lewis bases for each Lewis acid, which is really common, in which case you would make the coefficient the exponent. We also have the dissociation constant, so that's K sub D, where we do the opposite. We take the adduct apart. So the acid-base adduct becomes Lewis acid and Lewis base, and so that is the exact opposite of Kf. So Kd is the inverse of Kf. So this brings us to the coupled equilibria. We actually did this in chapter 13, so this is sort of a review, but we're applying it to new systems. We'll review what we knew from chapter 13 and then we'll move forward. So if you calculate the K for the overall system, and you've got more than one equilibria, if you change the direction of your equilibrium, take the inverse of the rate constant, because it's swapping reactions and products. So you swap the positions of those things in your rate equation. If you change the stoichiometry of the equilibrium, raise the constant to a new coefficient, or to the new coefficient. So if I multiply A going in equilibrium with B times X, then I would say B to the X over A to the X, which means that Kc is to the X. Simple enough. If you need to get the sum of interrelated equilibria, then you cancel the common terms and multiply by the rate constants. So if we have A and B in equilibrium, K1 is equal to B over A. If we have B and C in equilibrium, K2 is equal to C over B. And if you put those two equations together, you just add them. You have A plus B in equilibrium with B plus C. And the Kc for that is BC over AB. The B's cancel, and you end up with C over A, which is the same as saying K1 times K2. Our overall summarized thing is A in equilibrium with C, where the Kc is equal to C over A, which is also equal to K1 times K2. Okay, so let's apply this. All right, so let's try a coupled equilibria calculation. How many grams of chloride ions are needed to dissolve 1.0 grams of zinc 2 hydroxide powder in 1 liter of water? So we have a KSP of 3 times 10 to the negative 6th, and we have a Kf for zinc chloride of 1.6. So let's unpack this question in parts. It mentions zinc hydroxide, which we remember hydroxides are insoluble except when combined with group 1 cations, barium or strontium. And the constant we have for the solubility product of zinc hydroxide is somewhat tiny, like it's 10 to the negative 6. That's not a lot. We have chlorine ions, which are not a common ion for zinc hydroxide. So instead of talking about a common ion effect, we're talking about the complex formation. So we're given a complex of zinc chloride, or zinc 2 chloride rather, and the Kf that goes along with it. So we are going to start by writing both of the related equations, the dissociation equation here, right? So we have one zinc hydroxide making zinc 2 plus and 2 hydroxide ions, and we can write the KSP equation there. So we have zinc times OH minus squared. And we can also write the formation constant, right? So we have zinc 2 plus 4 chlorine ions makes this complex, and it's coupled with our Kf. Now, if we add both of these equations together, reactant side to reactant side, product side to product side, and then we multiply the Kf values times each other, as it told us to do in the coupled equilibria type problems, then we end up with the following. So we have zinc hydroxide solid plus 4 chlorine ions make zinc chloride, 2 minus, plus 2 hydroxide. And our K is 4.8 times 10 to the negative 6th. All right, so now that we have established this, we need to use it. All right, so we have that equation from the last slide, and we know that we need to solve for the grams of chlorine ions. Right, that's right here. We're solving for grams of chlorine. And where do we go from here? Well, if we look at this, that means we need to solve this equation that we just derived for chlorine ions. And so we can multiply our chlorine and then divide by our K value in order to isolate the chlorine. That's what we do. And when we actually solve for the chlorine concentration, obviously we're going to need to take the fourth root, but it's easier to plug it in not in the fourth root, so that's what I'm going to do. So what do we plug in? We need to start by looking at our problem again. So we have 1 gram of zinc hydroxide that we're trying to dissolve in 1 liter of water. So we should figure out the molarity of that if it actually dissolves, because we don't have zinc hydroxide in our equilibrium equation. It cancels out. So here we go. Well, not that it canceled out, but it's a solid, so it doesn't really matter. We're trying to dissolve all of it. So we take 1 gram, we divide it by the molar mass of zinc hydroxide, we divide by the liters in order to get molarity. So we get 1 times 10 to the negative 2nd molar zinc hydroxide. So if everything dissolves, that's what we'll get. But if it dissolves, it'll become ions. Okay, so that means since we have a 1-to-1 ratio of zinc, that we have 1 times 10 to the negative 2nd molar zinc 2 minus. But that's not in our equation either. Rather, it's the zinc chloride complex. So that's a 1-to-1 ratio as well, because we just have the 1 zinc in both. And so that concentration is 1 times 10 to the negative 2nd. When we go to do the hydroxide concentration, remember we're dissolving all of this per the problem. So there's 2 hydroxides for every 1 zinc in zinc hydroxide. So we multiply by 2, and we get 2 times 10 to the negative 2nd molar hydroxide. We can now plug all of this into our equation up above. And when we do, we get 0.86 moles of chlorine after taking the cube, or the fourth root, rather. When we multiply that by the molar mass of the chlorine ion, we get 3.04 grams of chlorine ions are needed in order to dissolve the zinc. Okay. So none of this was super hard, but there were lots of steps, and you need to be careful in your steps, especially with the exponents on your K values. All right, to summarize, formation constant, K sub F, is for the formation of coordination complex which contain a metal and ligands. Kd is equal to 1 over Kf. If you change the direction of your equilibrium, take the inverse of the rate constant, because it swaps the reactant side with the product side. If you change the stoichiometry of the equilibrium, raise the rate constant to the new coefficient. So if you did x times a, you would end up with a to the x power. If you need to sum interrelated equilibria, then cancel the common terms and multiply the rate constants together. Hopefully, you have a good idea of how this works now. I will see you in class on Wednesday.